Welcome back. Let's discuss this experiment 8, that is the up counter using behavioral modeling. So to model this up counter, so you have to know first of all what are the primary inputs and what are the primary outputs of the counter. So a counter will have clock signal, counter will have a reset signal, and a counter will have one output, that is count. So depending upon it's a 4-bit counter, 2-bit counter, so this size will vary here. Count size will vary. Okay. So again, those things are applicable that at the time of D flip-flop, what I have discussed, synchronous reset, asynchronous reset, active high reset, active low reset, pause edge clock, negates clock. All those things are valid for even for this counter. Okay. So what more here? This is up counter. So counter again, there are several counters by the way. You may have up count or you may have down count. You may have count, I'll list down here. You may have up counter, may have down counter. You may have up down counter, up down counter, up down counter. You may have count parallel load counter. So like that, there are several types of counters, by the way. The list will go on like that. There are several other counters too. So here, in our case, we are going to design this up counter. Okay. So it's a 4-bit, let's consider it as a 4-bit counter. So we will talk about the 4-bit up counter. It's a 4-bit up counter. So let's do that, how we write the code. So again, like you have to click on this model sim Intel FPGA icon. Just double click that. Then go to this jump start. There are other ways too that I already spoke, like going to the file, from there creating the project. So let's see this way. Create a project and give the project name here. So the project name is counter 4-bit up. So counter 4-bit up. Now you browse this. Listen carefully, everybody. You should not be working here. By default, whatever the path it is giving, there you please do not work. Browse it. And other than C drive, any other drive existing, there you work. In my case, I am doing it on my desktop. On my desktop, I have created already one folder, lab demos. Inside that folder, I'm going to create another folder with the same name. That is the project name. So project name is counter 4-bit up. Okay. Select that folder. Select that folder. And the other two things you keep as it is. Click OK. So now it will say like add items to the project. So we want to add this create new file. Click on that. Give the name, that is counter 4-bit up. So please avoid any kind of spaces here in the file name. And add file as type here. You have to select Verilog. Okay. So kindly avoid any other thing here except this Verilog. And then click OK. And we also require test bench file. So create and db underscore counter 4-bit up. Now add this add file as type here, Verilog. Click OK. So we have done with this two files are required. So we have done with that. Now you can close this. So now you just double click this one and the test bench file also. So here you will get those files here. This is the file that is counter 4-bit up.v, and this is the TB test bench file. So let's go to this file design file and let's start coding there. Module counter 4-bit up. Then open the parenthesis. Inside that, as I said, here you require to have clock, reset, and count. So here, what is required is clock, reset, and count. So terminate with a semicolon and the type declaration here, input, clock, that is CLK, reset, and your output here, output. And the size is 4-bit. So 3:0. This is count. This variable is count here. So semicolon. Now in D flip-flop also we said we require this always, that is procedural block always, and event control operator, open the parenthesis, pause edge clock. So this is active, positive edge clock based counter, and it is synchronous counter. So after this always, if multiple statements are there, we require to put begin and end. So here, if reset, we are checking if reset is high. The meaning of if reset means it is equal to like this. If reset double equal 1, you are comparing with 1. So here this double slash is for comments. If reset double equal 1, you are comparing. This is the equivalence checking operator. So instead of this, if you put this reset also, it is doing the same job. Okay. After that, if reset is high, then we are setting count to 0. So this I already spoke. There are two types of assignment operators. This one, if you are using, that is called blocking assignment operator. If you are using less than or equal to, then that is called non-blocking assignment operator. Non-blocking assignment operator. So here, when reset is high, we want to make our count 0. Else, so here, else, our count will be incremented by 1. So that is count less than or equal to count plus 1. So then semicolon. So you have done with this description, and this module we have to have the enclosure, that is end module. So now just save this file. Now go to the test bench. Here, let me copy this thing because that is required in test bench. Here, backport time scale 1ns/1ps module tb underscore counter 4-bit up. And then here paste that one what you have copied. And this one module name, this one should come after this input and output. And this input will become rich in test bench. And this output will become wire in test bench. And here you have to give space and then give the name DUT, that is instantiation name. So what is that? DUT here is instantiation name. Okay, that is user defined. You can give any other name too. Now here, initial, begin. $monitor is used to display contents in the console. dollar monitor. Inside the parenthesis, you have to write what is that you want to display. So I want to display time, and then that is a format specifier is required, and then clock percentage p, and then reset percentage p, and then we require here count, and this count I'm going to display in decimal. So percentage 0d outside of this double quotes comma. For percentage g, the corresponding is dollar time. That is system function which returns the simulation time. Remaining are here from export list. I'm copying and pasting them here. So now I have to generate my clock. For that, I am initializing my clock to 0. And I also initialize my reset to 0. And then this begin end. Now I use always hash 5 clock equal to negation of CL. So this is, I already discussed in the D flip-flop, that is experiment, I think this is experiment 7. There I have discussed. So about this, why it is required, there I have discussed. Kindly watch that. Now I have to take another initial. In that begin. So I know at my clock is going to happen at I mean positive edge going to happen at 5, because initially it is 0, then at 5 it is going to pick that positive edge. So before that positive edge clock, I'm making it hash 3, my reset 1, and then I wait till that pause edge occurs. Pause edge clock, and then I wait. After pause edge occurs, then I wait for 1 time unit. And then what I do is I remove my reset, because if I do not remove my reset, then according to this logic, always I will be seeing this count as 0. But I want to see this count happening, up count happening. So I have to remove the reset also after that, this pause edge. I mean, after this reset, I have to set it to 0 also. Now, how long I have to run this simulation means to generate with 4-bit, 2 power 4, that is total 16 possible cases, 0 to 15. So to generate all these 16 possible cases, I need at least 16 clocks. All right. So 1 clock on time and off time, if you see here, it is 10. So 10 time period is the time unit, time period of the clock. So in that case, I need minimum 160, means 160 into 10. At least 160 clock time units I have to wait. So what I will do is I will wait till 200, just 2 more clocks extra. There I am going to stop my simulation. And then this begin end. So that is done. After this begin end is done, this begin end is done, this module needs to be uh, closed with the end module. And module. Now save this one. Okay. So now go to compile all. Now here you just wait for this. So it is saying some error here. Let's see what is that error. So how to see the error? Here you just create a space in case lesser space is there. Then it is saying some error here in a counter 4-bit up in this file. 2 errors are there. Double click this. It will show up here. The illegal reference to net count. So, and line number is 10 and line number 12. So in this file, design file, line number 10 and line number 12, it is pointing here. So this I already spoke that Anything inside this always block, if you are assigning left-hand side, that must be of reg type. This why it must be reg type, I discussed at the time of this D flip-flop. Kindly watch that. So anything that is there on the left-hand side to which you are making assignment, and that variable is inside always, that must be of this type. Okay, that is variable type. In among variable, there are 5 other subtypes are there. In the design, it is reg. So save this. In the design means this is the design file. Save this and then compile. So now tick mark has come here, both successful here. Now go to simulate, start simulation. And here, as I told, you have to locate where the work folder is. Left to that work folder, there is a plus sign, expand that one. Identify which one among this your test bench module name is. This is our test bench module name. Select that, click OK. Now, wait for simulation tab to come here. So now your simulation tab has come. Here, TB underscore counter 4-bit up. There, you right click, add wave, you do it. Signals will be added here to the waveform. And now here this 100, you have to change this to this P, 100 PS. This P you have to change to NS and then run. So what happens is if you run, we are actually expecting our design to run till this 200. But here we are running up to 100. So better it is you make that at least 300 nanoseconds. Okay. Now click run. So now you are seeing your output here on the console, and the same thing in the waveform also you will see here. To get the full view, you click on this zoom full. Now you will have the full view. Now select your count here, that is count variable. Right click on that, go to radix. Here, take unsigned. Unsigned you take. Then you can see for every clock here, 1, 2, 3, 4, like that till 15. After 15, when you are trying to increment, then it is falling back to 0. So that way, this is simulation is like functionality check of the counter is done. Okay. So to close this simulation, go to simulate and simulation. And simulation, click yes. So now we have completed this as well. So next series will be on this schematic that is using LT Spice. Okay, thank you.